Okay, I think it's time to start. Any question so far? Okay, if no question, then let's keep going. We are a bit slower in our progress scheduling, but let's see. Okay, so we start with chapter 5, talking about orthogonality. So now we want to talk about geometry in our linear space. So we have distance and angle between our elements in our linear space. Okay, and to define those, first thing we do is inner product. So we start with our discussion. We are now limited in R. Okay. So we have inner product between two vectors, and in Rn they are like this. So you write the coordinate. So two vector and inner product is like you turn one of them into row vector and multiply with the column vector, and so it's just you multiply each component, so each coordinate is x1, y1, and adding them together. So plus x2, y2 plus data xn and yn. And this inner product, because we didn't really say, but it will tell you how close those two vectors are to each other. So we have been so the inner product will basically determine the angle between these x and y, and yeah, it's because this x inner product with y equal to x length times y length times cosine theta. So when theta is small, then the inner product is large, and so theta equals 0, then it's just equal to x times y. And theta equal to pi over 2, the inner product is 0. That's when they are orthogonal. And theta equal to pi, then inner product is minus x times y. Okay, that's the inner product. So now we know what's orthogonal. Orthogonal means the inner product equal to 0. Okay, and then we do a little bit of geometry thing, and we are stuck. Oh, okay. Recovery. Okay, I think we're okay. Let's see. Wait, Excuse me. Why is this weird? Presenter view. Maybe this one? Okay, seems to be working. Okay, sorry about technical issue. And yeah, so that's the inner product, and then there's a geometry thing. You can find projection on two places using these formulas, and you can find the projection onto plane, etc. And then we go to next section. We have orthogonal subspace. And orthogonal subspace is that well, two subspaces are orthogonal if every element inside them are orthogonal. So everything inside x and everything inside y have inner product 0. Okay. And so this is a stronger thing than saying the two subspaces are different. So the intuition kind of like, you think about in R2, maybe in R2, then you can think about like the two subspace. So a subspace by this line and a subspace by this line, they might be different. So those two subspaces no overlap because this line and this line only overlap is 0. But if you want orthogonal, then you need to be not have overlap, you want inner product 0. So orthogonal, you mean these two subspaces are orthogonal like this. Okay. And then we have example that saying orthogonal, so two plane that looks orthogonal is not even enough to say that orthogonal subspace, so you need the intersection to be actually 0. Okay, so everything inside needs to be orthogonal. And anyway, so that's orthogonal subspace. And then we define a complement of a vector space. This is like the biggest possible orthogonal subspace to a space, to a subspace. Okay, so we have some subspace Y here. So every subspace Y we can define a orthogonal complement to Y. Okay? And so this is basically the biggest possible orthogonal subspace to Y. Okay? So it's AVX. Okay, so O vector inside your Rn such that x dot t, x inner product with y equals 0. Okay, this is orthogonal complement, and we have some example. So say if your x is E1, then its complement is E2, E3, and y is E2, then complement is E1, E2. So we see that there is some kind of number rule, right? So you see the dimension of a orthogonal space plus its complement equal to this n over n. Okay, and this is a theorem we'll prove today, saying that subspace and its and its orthogonal component has a very strong property. One of them is the dimension is up to the dimension of the space. Okay. And then lastly, we prove the prove a little bit of property of orthogonal complement. So first is that any two orthogonal subspace, the intersection is 0. Okay, and that's just because the intersection need to have inner product with itself being 0, then it means to be 0, and then we prove that the orthogonal complement is actually a subspace. Okay, we've been talking about this orthogonal complement kind of like it's a subspace, but now we actually prove it. Okay, and okay, so let's review from last time. Any question? If not, okay, then let's go into more property about the orthogonal complement. But we need to go, so we are actually proving this in a bit funny way. So we need to go talk about something else first. So we back to rank nullity theorem again. Okay. So now we back to talking about the different fundamental spaces of a matrix. Okay. So we think about A is an n by n matrix as usual, and now we think about there is some B in Rn such that A B equal to Ax, and as we said, this Ax we can keep thinking. Okay, let's draw these ones. Do I have a space? Maybe. Okay. So this Ax, we can think A times X. So this x1, x2, dot dot dot. A times x is like first column times x1 plus second column times x2, dot dot dot. So A times x we all can always think as a vector that's a linear combination of the column vector of A. Okay, and this tells us that B is inside the column space of A, and this is actually if and only if. Okay. Okay. And now we think about A is linear transform. Okay, so the thing that we talk about this chapter. So now we think about A is a linear transform from Rn to Rn. Okay. And then linear transform has range and range and image, right? Range and pure image. Okay, so once again, range is there are no space and there are range of this matrix. But anyway, so what's the range? Range is all possible image of A, and that's exactly column space because we know every possible B is all possible linear combination of the columns. So the column space is a range, and okay, and then now the notation is a bit funny. Okay, So we are using different notation from the book. Book use R of A here for range, but we are saying it's column space of A. So to be consistent with the notation before, we have C of A here. But in some places you will still see R of A. So please point out when you see it. Okay. So I think like in some picture we still have R of A. But anyway, so we have the C of A as column space, which is the range of the linear transformation defined by A. Okay. So once again, range is all possible image of A. Okay. So you think about all possible X and what those column linear combination will map into. Okay. And so C of A is is the range of A, and as we said, is all possible B that got from B equal to X for some X, and it's a column space of A. And then we can think about, okay, so now we start doing something funny that we say we'll do. Okay, so we want to say the row space of A. Okay. And we actually say the row space of A by saying the column space of A transpose. So you do A transpose, you trans rows to columns. And so the column space of A transpose is similar. So it's all possible A transpose times X. So it's a column space of A transpose, and it's about the row space of A. Okay? And so why we want to do this, because we have we are being a little picky about our notation. So think about row vectors are actually like a n by 1 matrix that are n-tuple, and we are kind of thinking the row vectors are not in Rn, so we want to talk about vectors in Rn or Rm. So we need to do transpose first. Okay. So the column space of AT is kind of a row space of A, but we transpose the row into columns. Okay. So that all our vectors we talk about are column vectors. It's just a technical thing. Okay. Technical thing of how we define our notation. Okay. Anyway, so this is a row space. And yeah, so as we say, this is like a row space, so something inside it means if you transpose. So this is a row column vector, and if you transpose it back to a row vector, then it will be a row space of A. Okay, and okay, now we actually do something interesting. So now we want to think about null space. Okay, null space are what? Null space are vectors such that Ax equal to 0. Okay? Ax equal to 0. And now we think about another interpretation of this thing. If we think about A times X, is like you have rows of A and you have X here. And so each element is the inner product between each row and this vector. Okay? So this A times X is two different ways. We are doing two different interpretations here. So first we have this interpretation of it's a linear combination of columns, and now we say we are using this each element is the inner product between each row and this vector. Okay, and anyway, null space saying that n of A equal to so this X if is in null space, then this inner product with each row equal to 0. Okay, so it's orthogonal to to every row here, and so it's orthogonal to every column of AT. So the column of AT once again is like a row of A. Okay? And yeah, and well, if it's orthogonal to every basis element, it's easy to see that it's orthogonal to this whole space. Okay, so n of A is orthogonal to this column of AT, which is a row of A. Okay, this is a thing that we are going to base on. Any questions so far? Okay, and yeah, so now we're kind of connecting the nullity and rank thing to our orthogonal subspace discussion. So now we see those two spaces are orthogonal to each other. Okay, and actually it's stronger because null space is like everything orthogonal. Okay, and yeah, so So we have even stronger property. So they are not just orthogonal, they are orthogonal complement. Okay. So remember, orthogonal complement is like the biggest possible orthogonal subspace because everything orthogonal is inside. Okay. And yeah, so so we have that the null space of A is a orthogonal complement to this current space of AT, which is like the row space of A. And also, null space of AT is a orthogonal complement to current space of A. Okay, and yeah, and this is a fundamental subspace theorem, and the proof is pretty simple, I think. But let's see a proof. Okay, so first we have that. Well, here we already argue that null space is orthogonal to this current space of AT, and this means that it's inside its orthogonal complement. Okay, and this is just basically by definition because, yeah, basically by definition because we say this is the biggest thing that's orthogonal to each other. And but anyway, so we have like a very sketchy argument here. So let's see this in a bit more detail. Then we say x in n of a, then x equals 0, and we have y in current surface AT. Then y is is AT times on z. Then we have here we do inner product between x and y. So that's xt times atz. And then we can, by associativity, then we can put our parentheses around this xt, at. And that's actually axt. And we know ax equals 0, so 0 t times z equals 0. Okay, so that's an algebraic proof of what we argue with this intuition here. But anyway, we know that we know this thing, and then that means that nu of A is inside the orthogonal complement of C of AT, because the orthogonal complement is everything that's orthogonal to it. Okay. And then we need to prove that the other complement, right? We need to prove that everything inside this C of AT2 perp is inside N of A. Okay, so we have some x that's inside this C of AT perp, and by definition that means okay, and okay, this is not actually by definition, but okay. And then here we don't have algebraic proof, but you can think about how do I say? And that means AT this is a little trivial. How do I say this? Okay, I think it's easier to skip the middle. Okay, so if x is inside, I think this is back to this, so it's pretty obvious here. So if x is inside this. Okay, I guess. Okay. Yeah, sure. Sorry. Okay, so this is very easy, which I should not spend so much time. But anyway, so yeah, so here we are just checking. So x in CAT dual, and that means every x inner product with y needs to be 0 for every y inside this CAT. And now we just have y as every column of A, right? as a basism of CAT, which is all columns of AT. Okay, and so it's like X inner product with all columns of AT equal to 0. Okay, so this is X and this is AT, and we say X inner product with all of them equal to 0, and it's equal to this equation. So the first one will be this inner product with this, and the second one will be this inner product with this. Okay, so we can this figure out the X inner product with all column of AT equal to 0, and yeah, and it will be this equation. Okay, and so with this equation, and once again we do a transpose back, then we see that X equals 0 and X inside null of A. Okay, and so this is pretty trivial. And anyway, so the prover is saying that, well, null of A is everything that's inner product equals 0. So that everything coincide with this perpendicular, this complement need to be everything too. Okay, and yeah. So anyway, we got null space of A equal to complement of the row of A. And then the second one is basically you just change A to AT. Okay, so null of A. So we just call this AT equal to B. Then null of A equal to null of B equal to column space of B transpose complement, and B transpose is back to A. Okay, and yeah. Basically, we want to say null space is the orthogonal complement of the row space transposed. Okay. Okay, and let's see an example here. So we have an A that's very singular here. We have a 2, 0, and and so A is 1, 2, and 0, 0, and now think about the column space of A, and the column space of A, one of the column is 0, so obviously the column space is spanned by this 1, 2 vector, so column space is just 1, 2 times on alpha. Okay, and yeah, so that's a column space, so any vector B will be in this form, alpha times 1, 2, or x1 times 1, 2. Okay, and what about null space of AT? So yeah, so we want to check this thing. Okay, we want to check null space of AT equal to column space of A. Okay. Null space of AT dual equal to null space AT equal to column space of A complement. And okay, so column space is just x1 times 1, 2, because column just one non-trivial column here. And okay, so AT is 1, 2, 0, 0, and we want to find its null space. Then we solve the equation. Then 1, 2 times x1, 1, 2 inner product with x1, x2 equals 0, and you can solve this around, and you see that x1 need to equal to minus 2 times x2, and we call x2 beta. Then this is beta times minus 2, 1. Okay, this we have done a lot. And okay, so the null space of AT. Okay, and what's the range of A? Okay, so as we said, the range of A is the column space of A, and yeah, it's the thing we're already talking about. We have the calculate is alpha times 1, 2. And finally, we want to check, so those two subspaces are orthogonal complement to each other. Okay, and I guess we didn't quite prove this all, but we proved that. Okay, so here we only check we actually only check a part of it. We only check because we didn't prove that everything everything inside is like this. So here we check that C of A is orthogonal to N of AT. And that's just by taking inner product with the vector of this form and the vector of this form. Okay? And yeah, so alpha times 1, 2 inner product with beta times minus 2, 1, and then it's 0. Okay, so we see that current space of A is dual to null space of AT, and then you need to actually say dual, then you need to say everything is inside, and you need to run the previous argument. Every orthogonal thing is of this form, and it's like kind of a trivial argument. Okay. Question so far? So this is extra feature of the rank nullarity thing we know. Okay. And now we back to our, okay, so now we finally connect to our rank nullarity thing. Okay. and from the thing previously before, then we can say that it's kind of the other way around. Okay. So because of this theorem we have here, then combined with the rank nullarity thing, we can say that dimension of S, so any subspace S, and plus the dimension of the orthogonal complement is equal to the dimension of the parent space Rn. Okay, and also if you have a basis of S and a basis of S dual, then you just list them together and over basis. And intuitively, we have seen a lot of examples. That S is a span of E1, then S dual will be a span of E1, E2, E3, and in R3, and so 1 plus 2, 3 is equal to N, and the base is E1 here, and the base is E2, E3 here, and together E1, E2, E3 is the basis. And we say that that is more general. Okay. And the proof sketch is that, okay, so detailed proof, so I think here now we want to keep the schedule a little faster. So the detailed proof, you can check the book, but here we provide just a little sketch. So the sketch is you want to use a previous theorem and rank nullarity thing. So you try to put this S and S dual as the row space and null space of matrix. And what's the matrix? The matrix is so you find the basis of your space S first, and so you list the basis vector together and call that matrix. Okay. And so we consider this matrix. Then so what's S? S will be the current space of X, right? Because S is well, this is like by definition. S is all the linear combination of the basis element. And the current space is the linear combination of all the current vector here. Okay, so S is just the current space of this matrix X here. Okay, and then also, and what about S dual? Then we can use the theorem before, so we know. Okay, so S is the current space of X, then S dual will be the null space of X transpose, just because the thing we have here. Okay? Yeah. So S is C of A, and we know that S dual is the C of A dual, then it's the null space of X transpose. Okay. And yeah. So that's a null space of X transpose. Then we back to rank nullarity. Then then we know the dimension of this null space of X transpose equal to the dimension of the row space plus the dimension of the row space of X transpose equal to n. Okay, so this thing plus this thing equal to n. So dimension of S plus dimension of S equal to n. Okay, so yeah, that's how. Okay, and so that's how. Okay, so this is. Personally, I don't like it. It's a little funny way to prove this, but this is how we show that this kind of completeness property of the dual space and complement space and the subspace. Okay, so the dimension a to n. Okay, and okay, the dimension a to n. Then we can prove that those two. We can prove that if you're listing the bases together is also a basis. Okay, so we already know. Okay, okay, yeah. So we know dimension n dot to n, so we know there will be n vector here. Okay, there will be n vector here, and then we just need to prove that they are linear independent, and that can be pretty easy proved by knowing the second complement. So like you just have all the c plus all the c equal to 0, and yeah, you can show that they are linear independent because basically, well, these bases or inside each they are already linear independent, and you think about you want to write say xn as a linear combination of x1 to xr. Then it's not possible because it's orthogonal. Okay. Okay. Yeah. Yeah. Okay. Okay. And that's the star of our theorem. And so now we have this interesting definition that's that's this direct sum of two space. Okay. And the definition written here is a bit funny. Okay, but anyway, so we are saying that we have two subspace of W, and and then. We are saying if W then and if they have this nice property that everything that W can be written as oh, I forgot to update. Anyway, let's do this uniquely. Okay. And yeah, so we have U and V. Yeah, so we have two subspace, and we say W is the direct sum of U and V if U and V kind of together become W. That means that everything inside W you can write as U plus V uniquely, where U is inside U and V is inside V. Okay. And yeah, so once again, a good example is, I guess later we'll have more example, but a good example of the U is span of E1, and V is span of E2, E3 for R3. Okay, and so every vector inside W can be written uniquely as some A1 times E, some X1 times E1, and some X2 E2 plus X3 E3, right? Okay. Okay, and yeah, so we call this direct sum. But so what's funny here is by the definition here, U and V don't need to be orthogonal. Although most of the time we are thinking U and V orthogonal. Okay. Okay. And so while we're talking about this, we were talking about second complement because we want to say orthogonal complement they direct sum into the parent space. Okay? And yeah, so here I think we skip the proof, but yeah, it just give you some intuition. And as we see, so you have the example U and the V here, and they also going to complement and they add up to the whole subspace. And I think the proof can be pretty easy getting from here. Okay, and it's just that we know this thing is a basis, and so everything inside. So everything inside Rn you just uniquely express into linear combination into this basis. Okay, and okay, yeah. So you see some subspace, and there is also going to complement really describe the whole space nicely, because it's kind of you can partition the Rn into those two spaces that orthogonal to each other, so they are like two separate parts, and you can think about, so every vector in Rn you can think about its component in S and a component in S2, and it's uniquely expressed. Okay, so that's 5.2.3, and yeah. And also, you can prove that if you take the complement of the complement is back to a subspace, so it's kind of a symmetric. So yeah, so I think probably a mental picture I have is that you can kind of think Rn into this space, and then every space you have you can cut Rn into, well, sorry, this is a bad choice. Don't forget about it. Okay. Yeah. But yeah. Yeah. So the complement of complement is a space, but I guess something hopefully not too confusing to you is you need to be a little careful. Wait. Yeah, I think we have this, right? I think okay, hopefully this doesn't contradict with the notation with our homework. But what I want to say is, so the direct sum is not same as the union of those two subspaces. Okay. So so everything can be written as a linear combination U plus V. Doesn't mean everything is inside either U or V. Okay. So W is not in the union of U and V, because the union doesn't contain, say, U and V like this. Then you have vector E1 plus E2. That's neither inside U and neither inside V. Okay. It's just a small thing that you'll be a little careful. So they can be written as something inside U plus something inside V, but the U and the V union is not the whole space. Okay. Yeah, so just a little thing to be careful. But yeah, but we know that. Okay, but okay, that's once again reminder of all three theorems. So orthogonal complements, kind of divide up the dimension of Rn into two parts. So they or kind of divide the basis into two parts. So so the dimension add up to this whole Rn, and and then everything inside Rn can be written as something in S and something in S dual, and uniquely, and also the dual of S. I keep saying dual, actually complement. The complement of S complement is back to S. Okay. And yeah, this is what the thing we just said. Okay. And we have other thing. And yes, and by this complement being back to the same thing, then we can write a little more 5.2.1. So we can have the complement of null space equal to the row space or column space of AT. Okay. And okay, questions so far? Not? Okay, then let's keep going a little bit. Excuse me. Okay, so once again, X equal to B is consistent if is inside the column space of A, and column space of A equal to column space equal to the complement of null space of AT, and so we have that. Maybe it's so we have this corollary saying that if we have an arbitrary vector b, then either A is equal to b, b, which means that it's consistent, or when it's not consistent, there is y such that y is inside null space, and y inner product with b not equal to 0, and this is okay. So it's easier to see this. Okay, so we are saying we can so for whatever b, we can separate it into because the null space and the row space okay, so it's actually C of A. Okay. So this is C of A. Sorry, not row space. This is one where we should say C of A. Okay. So column space and null space of AT span the whole space. Okay. So we know Rn. Okay. So the space is Rm here. So Rm equal to column space of A plus null space of AT. Okay. And so every vector B can be written as some component inside column space plus some component inside null space. Okay. And so there are two things. So it's either the component on the null space is 0, then B is inside this column space. And if it's not 0, then you have this component here, and this component inner product of B will be non-zero because the inner product is linear, and so inner product of B will be inner product with itself and the inner product with some component in the column space. But y inner product with this column space equals 0, so it's just y inner product with itself, and that's non-zero. Okay, so that's something. And anyway, let's back to some calculation. Okay, so this is something that we already know how to do before midterm, and let's do this once again. So I have A, and we want to find a whole bunch of a basis for a whole bunch of space. So the null space and the column space of AT, and so the null space and the column space and the column space of AT and the null space of AT. And to do this, then basically you do the Gaussian elimination twice. So you can do Gaussian elimination for both A and AT. Okay, so you do Gaussian elimination for A, and you get this, and then you get Gaussian elimination for AT, then you get this. Okay. And so null space, we have known this from chapter 1. So we have a Gaussian elimination from here, and then we found null space by solving this ux equal to 0, and that give you those two equations: x1 plus x3 equals 0, x2 plus x3 equals 0, and so we just say that x3 is free variable. Back to this thing. Okay, so we just say x3 is a free variable here to some x3 or some alpha, and then in case of x1, x2, and you say the null space is spanned by this -1, -1, 1. Okay, and okay, and then we do this funny. Okay, so actually now we can find both those already, right? If you remember what we do in chapter 3, okay, from just this equation. Okay. Anyone want to answer? So, what's the current space of AT from this thing? Okay. Okay. And so current space of AT. So this is like our midterm question. So current space of AT is the row space of A. Okay. And row space of A is row space of this thing, so it's spanned by those two things, but you need to transpose. Okay, but you need to transpose, so it is 1, 0, 1 and 0, 1, 1. Okay, and yeah, so those are row space, and you transpose, then that's the concept of AT. And also remember, we can also find the current space of A from this thing. We can just look at the pivot. It is 1 and 1 here, and we know this 1, 0, 1 and 1, 1, 3 forms the basis for the current space of A. Okay, and but we can also see that from this is the 1, 0, 1 and 0, 1, 2. And you see that this thing is just the second column minus the first column. So yeah. So the span of those two things is same as the span of those two things. Okay. But anyway, we do this in a stupid way. So we do because we want to find null space of AT. I don't think there are smarter way. But anyway, yeah. And okay. So we actually already know the current space, but we still want null space AT. So we have yeah. So I guess it's a good question for you to think whether you can get null space of AT from just this thing easy. But anyway, we can transpose it and do another another Gaussian elimination, and then we can calculate the null of AT once again by solving the equation, and we see the span of -1, -2, 1, and column of A, as we say, is it's a row space of AT transpose. So we get those two rows transposed, and they become a basis for current space of A. Okay. Any question? And not okay. So here we have a little checklist. Yeah. And so remember orthogonal subspace. Subspace is that everything inside X is orthogonal to everything inside Y, and then orthogonal complement is like the biggest possible orthogonal subspace to a subspace. And then we go back to matrix a little bit. Then we see that the null space and the transpose of row space are orthogonal complement to each other. And then we prove a bunch of things about direct sum. So we see that the orthogonal complement let direct sum into the parent space, and the complement of complement is the previous space, and the direct sum to the parent space, so the dimension sum to n, and yeah. So dimension sum to n, and the direct sum into the parent space, and the complement of complement is the original space. Okay. And and the algorithm, you do Gaussian elimination once again. And then finally, you have the picture here you can stare at during a break. Okay, let's have 10-minute break.
因为好像有看懂它字面的解释，但没有很就是理解太懂，就可以举个例子。然后
就是例子就是刚刚那个1 跟1 2 1 3嘛。所以你的 U 就是我想想看，用黑板写好了。所以你一个 vector 三个 dimensional vector， 我们这里没有粉笔吗？所以说可能用的 U 是1 然后 span V1，然后 V 是 span of 1 2 1 3这样子比较容易懂吧？画图比较容易懂吗？那就是说，我想想看，我换一个，把它反过来，我们这样子比较好画图。所以 U 是1 3，然后这里是1 1 2这样子。那就是说，我们三个 dimensional 的 vector，所以 U 是这条线，然后 V 是 x y 平面。对。那我们说什么？我们说他们是他们 direct on to whole space，那代表说 我们随便一个 vector 都可以拆成我 project 到 U 上面的分量，虽然我们还没有教怎么做 project， 但你可以想象，对，我们 project 到 U 上面的分量跟 project 到这个 V 上面的分量，然后这两个 vector 的这个 projection 是 unique 的这样。然后对，然后对，但是这个定义这里没有要 unique，所以有点奇怪。如果要扯多一点的话，你可以想象说，照这个定义走的话，可以想象我在 dimension 2上面有一个 U 在这里，V 在这里，然后不见得是个脑袋，但是你也可以说我们任何一个 vector 在这里。OK， 可这个可以拆成这个分量跟这个分量的感觉吗？就有点像你在拆 basis 这样。对，德瑞上基本上就是在说这个，他们的 basis 合起来就会变这个 space 这样。应该说有两件事吧，他们 basis 合起来要 span 整个 space，然后还要说他们没有相交，对，就是例如说，如果你的 U 是如果你的 U 就是这 uniqueness 的事情，所以如果你的 U 是1 2 1 3的话，应该说你的 U prime 是1 2 1 3的话，那就没有了，因为如果你的 U prime 是这样的东西的话，那你在1 2上面分量，你就可以把1 2丢到 B 或者 U prime，那这样就没有 unique 了。所以要刚刚好的变那个 space。
是的。
Okay. Hello. I guess let's write this here. Okay, let's talk a little more about second complement. Okay, so maybe give some idea about second complement. So I think a good way to think about second complement is actually this thing. Okay, so you want the basis of S and the basis of F dual together is the basis of Rn. Okay, this is a good way to think about second complement. So you want so we say U and V, the union together doesn't become W, but we want basis of E, basis of U union basis of V become a basis of W. Okay, and or let's talk about Rn. Then we want the basis of S union basis of S dual. S complement is the basis of Rn. Okay, and so we want let's see how we write this. Maybe we have x1, x2, xr, and s equal to I guess let's go into example first. Okay, and so let's have an example in example of R3, and not like this, R3, right? And so on previous page we have this U is spanned by E1, and I guess that's okay. Okay. Actually, let's change this a little bit. Let's say just like what I have on the blackboard. Okay, so we have a U equal to E3, and V equal to span E1, E2, and this will mean that R3 is span E1, E2, E3, and is the direct sum of U and V. And you can kind of think it this way. So we have this three-dimensional space, and and the U is this line. U is the span of E3, so it's the z-axis, and V is E1, E2, so it's the xy plane. Span by E1, E2 is the xy plane, and so you have whatever C vector here in R3, then you can write in component to U. So it's a Z component and it's a XY component, and this is a unique decomposition. Okay, and so we say the union of the basis of U and the union of basis of V should be should be a basis of W here. And so then what are the best things can happen? And so basis, there are two things you need to check, right? You need to span the whole space, and they need to be linear independent. Okay, and yeah, and those two things correspond to two things here. So linear independent will give you unique, and then okay, and okay, so there are actually two things I should mark. So we have the each or here. Okay, so so you need space need to be linear independent, so you have unique, and then the union basis need to span the whole space W, so that everything inside W can be written. Okay, and so some example that doesn't satisfy those is you can think about we have a U prime, say equal to span of E2, E3. then then we have then R3 is not equal to U prime the rest on U because because we have the E2 overlap here. So if you have a basis that union of all those four vectors, then well E2 is obviously not linear independent to E2. So that's another, those four vectors is another basis for R3. Okay, and that will mean that you lose the uniqueness. Okay, you will lose the unique here of the uniqueness here of this decomposition U plus V. And then if you want to lose the whole thing, then maybe let's say you have a V prime here, is a span of just E1. Okay, and then you also have that R3 is not equal to U the rest on with the V prime. Okay, that's because U the rest on with U prime only span things inside E1 and E3, so they only span the XZ plane. And well, so this thing is a span of, so this is another subspace E1, E3, right? And yeah, but that's not the whole space. Okay. Yeah. So yeah, so for those to be direct sum, you want the basis to be linear independent to each other, and so basically no overlapping in the subspace, and also you want so you want no overlap, so you have it uniquely, and also you want basically together to span everything, and yeah, span everything then can also get them from this thing. This kind of thing. So you want U and the V, then dimension are to add up to the dimension of W. Okay. Okay. Clear. Okay. Hopefully this is clear. And if this is clear, then we can go to a bit of applications. Okay. Let's see. Can I do this? So keep int notation, and we'll open a new PDF. No, okay, this one. Hopefully. Oh. So that's okay. Let's save here. What is okay, and this. And where? It's weird. Let's see. Okay. Things were okay. Yeah. And I guess a little review. Oh, I should say the picture. But anyway, a little review about all the matrix spaces. So, n by n matrix may be from Rn to Rn, and you can think about you change is Rn equal into two parts, so it's like a row space, something in row space or the current space of AT, and then we know, and the null space part. Okay, so we know those two things are complement, and they add up to a dimension. And so this and the dimension rank is R here, and the null dimension is rank. Null space have dimension n minus R. And when you got mapped to Rn, then everything inside null space will map to 0. And everything inside this row space will map to the column space of A. And this is also dimension R. Okay, so dimension R map to dimension R. They actually do mapping, and this dimension n minus R just go to 0. And then there is a weird part that's null of AT, that's a complement to this column space, and that just things that they will never reach by having A. Okay, and also if A is non-singular, so you have n equal to m and A is non-singular, then just you have no null space and no null space of AT. Okay. Then you can just go back and forth between column space and row space. Okay, and okay, so that's yeah, that's about characterization of matrices. And now we go to a very different thing. I guess not so different, but but I guess the first specific application of linear algebra, that's solving a least square problem. Okay, and so this is really application. We want to do something that we want to solve. Basically, sometimes we have some experimental data and a whole bunch of points, and we want to find a curve that fit the point space. So sometimes you have a linear approximation or a polynomial or something that fit your data point. Okay, and okay, so maybe let's draw a picture here. So the idea is that you have whatever point that's like your experimental data, right? Like this, and then you want to say, I think this is predicted by one line, but the points are not actually on the same line. Okay, and but you still want to find something that you think is based, and so a conventional way to do this is you want the sum of square of area, so the area from your point to so the distance from your point to the line, you want to the sum of square of those areas to be minimized. Okay, and then this kind of problem can be a lot of time that can be formalized as our linear system. It's over-determined linear system equation. For now, we will not show how to transform from this problem to our over-determined linear system, but we'll have an example later. Okay, but for now, let's just take as granted that we want to solve with this over-determined linear system. And what do we mean by over-determined linear system? So linear system is this Ax equal to b, and over-determined, so n bigger than n. So we have more equation than unknown. So n bigger than n means your A kind of look like this. Okay, so A is like a lot of columns, and x is shorter, then you have equal to a long vector b. So n bigger than n. Okay, so you have more equations than unknowns, and you have more equations than unknowns. So a lot of time the system cannot be is not consistent. Okay. Yeah, so yeah, usually it's inconsistent. Okay, and okay, so A is equal to B and is inconsistent, so you cannot really solve for x satisfy this. And but we still want the base x in some sense. Okay, you want x in some sense that give you base x equal to b. Okay, so you want to solve x equal to b, but you cannot have this exactly. So okay, so we define this residual is as how much area our x. Excuse me. Okay, yeah. So you cannot find the x such that x equal to b exactly. So we study how much closer, how close we can get to b. Okay. So we define this b minus ax as a residual, and we want to find the x that minimizes this residual. Okay. And that's the mathematical problem we want to solve in this section. Find x such that b minus x is r of x defined as, so obviously depend on x. So b and a are kind of constant given. And so this is a function of x, r of x, equal, so this is a vector in Rn. So b minus x, we want to minimize, well, it's a vector, so we actually want to minimize the norm of this vector. Okay, so we want to find x such that norm of r of x is minimized. So we want to minimize the norm of b minus x when choosing x. Okay, and it's a little easier to think about r of x squared. So obviously a norm is a positive number, so minimize the norm is just minimize the norm squared. Okay, and then we will use this notation x hat. We'll see a lot. So this x hat. If x hat minimize your r of x squared, then you will say it's the least square solution. Okay. So yeah. Yeah, kind of a square from the square here, although it's a bit funny because by this formulation here, you can also minimize the non-square thing, but there are reasons that it's called least square. And anyway, the name is called least square solution, and it's a solution that minimizes r squared. And if we find the solution, then we call it x hat. Okay. So x hat is x such that it minimizes b minus ax. No. Okay. So far is the definition. Okay. And okay, so now we start to think about how we solve this. Okay. So the first thing we observe is that, well, ax hat is inside the column space of A. Right. So we think about, well, so I think the idea here is we want ax to be close to b. So first we think about where we can get ax into, right? So ax, once again, is inside the column space of A, right? That's just what ax is. Ax is a linear combination of columns, so it's inside column space. Okay. Yeah. And so if we want ax equal to be close to b, then we want to find things inside the column space that's closest to b, basically. So now we think about geometrically. So this ax is everything inside column space, and then we want to find it close to b. I think we can cheat a little bit. Okay, so it's like this idea. So okay, so this is actually column space in the row space once again. So this is C of A. Okay, C of A here and C of A here. Okay, and yeah, so we think about ax is inside the column space, and you have some b that's outside the column space. So b is not consistent, but you can find some point that's closest to b inside your column space, and the point we call it p. And we'll see that this p is exists and is unique. Okay. And but well, I guess geometrically that already makes sense, right? So you have a space here, and you have some vector outside, and then you you can always kind of project a vector onto your space, and then find this unique point that's the closest point to your vector. Okay, that's what we will do. Okay, so that's a little spoiler. Yeah, it's easy and it's unique, and that's a theorem. So we have okay. So now we forgot about A a little bit, and we just think about the column space of A. So here we have we think about A is equal to column space of A. Okay. And but we write the theorem in very general form, so we just have whatever subspace, okay, and we have whatever subspace of Rm. A little confused. Okay, yeah, Rm. We have whatever subspace of Rm, and we say then we have something that might or might not be S. So any space in Rn and there is a unique point P that's closest to B. Okay, that is P in S that's close to B. That is everything that is P in S will be further away. Okay, and and also vector also this P. The P is the closest point if only if B minus P is in S still. And I guess I should write it here once again. So I'm saying, you are saying, so you have a subspace here, this S here, and you have a vector B here, and we are saying there is a point P here. Okay, point P here, and then we are saying the P is the closest point. This closest point exists, and when it happens, then you have this B minus P, which we actually call Z here. Okay, Z later. So we are saying the Z vector, if the Z vector is orthogonal to P vector, then this P is the closest point. And yeah, so if you just think about geometrically, it's kind of trivial. But let's write down our equation. Okay, and so we now use the thing we just talked last class. We have S, and if we have S, then we can always find S complement. Okay. And we know that Rm can be written as the direct sum of S plus S complement. Okay, and yeah. Okay, so Rn is the direct sum of S and S complement, and now we use things nicely. The theorem we didn't prove, okay, but we're still going to use it. And the theorem is that everything inside Rm, which is B here, can be written as uniquely expressed as some P plus Z, where P is inverse S and Z is inverse S dual. And yeah, so P plus Z and P will be your closest point, and Z will be something orthogonal to P. Okay. And okay, so now we have a pretty trivial proof now. So now we think about we have another point Y. Okay. So first thing we want to say is if we have another point Y. Oh, sorry. Another point Y here, then so we have some Y here. So you have another point Y inside S, and it will not be closer to B, and that's because so you can kind of just see geometrically here. So the distance from Y to B will be the square of the distance between Y and P plus the length of Z square, and so that's longer than just the length of Z square. Okay, and I think we can skip the detail. So yeah, so this is exactly what this right now. So distance from B to Y is because of the orthogonality here is distance from Y to P plus distance to Z, and the distance from Y to P distance from Y to P is non-zero because Y not equal to P, and so the distance from Y to P is non-zero, and so the distance is bigger than just this Z square. Okay, and then we have the other part, which is looks very seems a little tautology, but need a little bit of proof. Okay, and but so now the notation is a little overloaded because we talk about P in multiple things, although we are going to prove that all the same P. Okay, and okay, so on the first page here, we have a P that's a unique decomposition. That's unique decomposition. That's B equal to P plus Z with P inside S and Z inside S dual. Okay, so it's this thing. And now we want to prove the second part of the statement, which says that every vector P is so yeah. So we are now overloading the P here. Okay. So kind of think if there's another vector, let's say it's a p prime, maybe that's a little better because it's really confusing. So we have some vector p prime. Okay. We want to say the p prime is the p that we found before, and basically we just do this by the uniqueness of the decomposition. Okay. And yeah, so we have another vector p prime, and that's we say p prime equal to p, if only if b minus p prime in S dual. Okay, and okay, yeah, so we have p prime here, and yeah, and so just by uniqueness of the Dirichlet decomposition, remember we say everything. So this b, if we write it in terms of this p plus z, and this is unique. This must be unique for it to be a Dirichlet. Okay, and so if p prime has this, we have p prime plus b minus p prime also equal to b, obviously. And p prime in S and b prime is in S dual, and because this decomposition is unique, so p prime must equal to p, and yeah, so p prime equal to b, and that's the closest point to b. Okay, is a lot of notation to say something a little dumb. Okay, and then we want to say if only if, and we can also do the similar argument, and so the other way is you have some Q in S, and and such that B minus Q is not in S dual, and then then obviously Q is not equal to P, okay? Because because we know P is satisfied this also in S dual. And yeah, so obviously Q is not equal to P, and well, then Q is not the closest point because of the previous argument. Okay, okay, and yeah, so anyway, we see that the closest point is this unique point such that B is decomposed into the S component is a unique S component of B inside S. Okay. And okay, that's nice. And let's see a little more. Okay. And so easy case. So now we kind of want to find. Okay, so we have some characterization of B, but P, and we still want to find it. Okay. And anyway, let's see some characterization first. So if our system is consistent, so B is S, and then it's easy to find P, because P is just equal to B and Z equal to 0. Okay. And then we have the RNN. So now we go back to solving linear system. Solving the least square problem. So now we want to find the closest point of A is equal to B. So now back to S is the column space of A. And yeah, and yeah, so that P will be the P will be the X, and so P will be A times the X hat. Okay, because yeah, that's the base solution. So yeah, we want to find the closest point in C of A, that's to a B, and that will be the P, and that will be A X hat. And now we have moment, so P is called the projection of B onto C of A, or yeah. Okay. And yeah, so we are now back to this page. So we have some example of projection. So if C of A is a two-dimensional space, and B here, you project here, and yeah, also this. And yeah, and we see that by our characterization before, then we want this. well, obviously b minus p is just this residual of x, and we want to minimize this residual of x, and it's inside the dual of c of a. Okay. And yeah, so finally we find this condition. So we want to xk to be the solution to our least square problem. Then we want r of x hat is inside the dual of column space of A. And now we go to how to solve this. How to solve this is okay, we want r of x inside C of A dual, the C of A complement, sorry. So yeah, once again from this picture, we want r of x inside C of A complement. And finally, we can use our regularity thing, and then we know that C of A complement is the null space of AT. Okay, this is the thing we just talked about this lecture. And so now we change our condition to that r of x inside null of AT. And so we rewrite this again. This means AT times r of x equal to 0. So AT times once again, and we write back what's our r of x. Our r of x is b minus ax. Okay, and yeah. So finally, oh, here I'm losing sorry, b minus ax hat. R of x hat is b minus ax hat. Okay. So now all the algebra we arrive at. So now move things around. So we want to solve this ax hat, and finally we arrive at this nice equation. Okay. So we have ATAX equal to ATB because, yeah, so we just multiply this out and move ATA to our AX to the other side. And so this is the equation we need to solve. We want to solve ATAX equal to ATB or ATAX equal to ATB. So yeah, so A and B are given, so you can just calculate ATB here. And so this is basically a linear seesaw equation, right? So you have ATA. Okay. You have ATA here, so you can kind of group things together. You have ATA, some matrix you can calculate is n by n. Oh, sorry. You have ATA here, the sum matrix you can calculate is n by n matrix, and you have ATB, that's a dimensional vector. You can calculate from A and B. Okay. And so this is called a normal equation. Well, and yeah, so now we are back to solving linear system equation, and so you can do Gaussian elimination, etc., and to solve this. Okay, and it's possible, although not very likely, to have more than one solution. So if your ATA is singular, then you have more than one solution as usual, right? And okay, so if ATA is singular, so it has no space, then you have more than one solution. Although it should be rare, but oh, here we are having the difference of R and A and C of A here. Okay, and so this is C of A once again. C of A. Yeah. Yeah, and so if this is singular, then it means that you have more than one solution to your least square problem. And but we say the P is unique, and that means that X hat and AY hat is both equal to P, and well, that's just what happened. And but what about when this is non-singular? When we mean non-singular is when A has rank n. Okay, so remember n bigger than n. So rank n is A is the largest rank. So A look like this. So m and n, and well, rank cannot be bigger than either m and n, and so largest rank of A is n. So it means that every column is linear independent. Then, and in this case, we actually have a unique solution because you can show that when A has rank n, then ATA is non-singular. Okay. So A is like this, and ATA, well, ATA, so this is A, and ATA is like this, ATA, and it's n by n matrix. And anyway, we have a proof sketch here, and you can show that ATA will be non-singular if if A has full rank, and if it's non-singular, then you can just solve this equation by -1, right? So you have a unique solution x hat that's equal to ATA -1 times ATB. So yeah, so if you forgot all the derivation, you can still kind of memorize this equation and solve for least square, a lot of least square problem. Okay, and that's kind of what we do. So yeah, So this x hat equal to ATA -1 ATB is a solution to our least square problem. We have a long derivation involving analysis about the column space and the residual, etc. Okay, and anyway, the the conclusion we have that is xk equal to ATA -1 ATB. And now we can do something a little dumb. That is, we want to find what's the p here, and so p actually have an even longer equation, and so if you want to find p, you just multiply the a back, because remember p is a times x hat, and somehow we end up with this really long equation. P is equal to a times ATA minus 1 times AT times b. It's a really long equation, but that's b, and it's an element of C of a once again, C of a, and that's the closest point B that we're talking about. And this really long matrix we call is called a projection matrix, ATA -1 AT. And okay, any question from this really long derivation? If not, then let's do something I think is a little easier. Let's do kind of brainless calculation now. We have a formula, and we know how to calculate everything here. So we need to do matrix transpose, matrix multiplication, and the matrix inverse. Then we can find everything we want. Okay. And so we have want to find a least square solution to this thing. So as we say, we have more equation than unknown. Okay, so this and we'll have this inconsistent. And so we write this as a is equal to b. Then a will be this 1 1 minus 2 3 and 2 minus 1. And b equal to 3 1 2. Then we can calculate AT easy. You just flip this around. Okay. So 1 minus 2 2 become 1 minus 2 2, and 1 3 minus 1 1 3 minus 1 here. Okay. And AT. And now now we can do plug in formula. So normal equation. We actually don't do the most usual, most powerful one. Although you can kind of check. So here you can feel that those two columns are linear independent. So you can actually do the ATA -1 equation. But we do the normal equation, which is you might have more than one solution. Okay. So we want the ATA x equal to ATB. Okay. And I guess maybe a way to memorize this is think that this is just A is equal to B, and but you multiply AT on both sides. Okay. And anyway, so A is equal to B, and then multiply AT on both sides. And so you can calculate ATA here, and this will be this 9 minus 7 minus 7 11 matrix. And I guess the thing to check here is 2 by 2. Now it's a smaller matrix. So we reduce the number element here. And it is resolvable now. And also you have ATB here. So yeah. So instead of 3 equations, now we have 2 equations here. And now we can find the solution. And yeah. And the solution here, we have a terrible number. And it's this thing. But yeah. Solving linear system, we know a lot. Okay. So yeah. This is how you can solve a linear system equation. Instead of ax equal b, you have atax equal to atb, and you solve this equation. Okay, any question so far? Okay, if not, then then let's see how this relates to the thing we talked before. Okay, we have example that's that relate to our motivating example. So we say we have a table of data, so we have a whole bunch of x and y, and we want to find a linear approximation to those x and y. Okay? So we have a lot of endpoint, x1, y1, x2, y2 to x and yn, and we want to say x, y are linearly related. So y equal to some c0 plus c1x, and we want to find the beta base physics in least square sense. Okay, and how this work is that so we write for every y. Okay, so y equal to c0 plus c1x. So for every yi here, they need to be equal to 0 plus c1xi. Okay. So y equal to 0 plus c1 xi for all endpoints, so I from 1 to n. And you can write this in linear system equation with this funding matrix. Okay. So so you want to solve for c0 and c1. So 0 and c1. Okay. So it's a little confusing because we have been using x as a variable here, but so now the unknown variable to solve is actually 0 and c1. Okay. And then the x is actually become part of your a. So you have this 1, 1, 1, 1 and x1 to xm as your x matrix. And this a matrix times the c0, c1 should be equal to your y vector. And so this equation will be so this equation will be like trying to satisfy all those equations, right? Because like the first element will be c0 times 1 plus c1 times x1 and equal to y1, etc. And yeah, and as we see, there are m equations but only 2 unknown. So generally this is not solvable unless actually all the xi equal to 0. So sorry, all the yi equal to 0 plus c1 xi. That's not very likely, but we can find the least square solution. Okay, so we can find a solution such that the square of this difference is minimized. Okay, so yeah, and you can kind of see the so now we have R of Ci, right? Let's wait, sorry. Okay, and let's write a little more. So now we can think about, so R is the vector of the difference. So we want to minimize this R of C vector and square, and that will be some I, this yi minus c0 minus c1 xi. Oh, I should write only 1, but anyway, square. Okay. So yeah, so that's why this is least square. We'll minimize the some squares of the errors. Okay. And yeah, let's see some example. So we have only 3 points here, so it's easier. So x 0, 3, 6, and y is 1, 4, 5. We don't have a picture, but you can kind of imagine yourself. So we have a 3 point that's not really on a line, but want to fit it to a line. And so we do the thing we said before. We want AC equal to y, where A is 1, 1, 1 in the x vector, and C is just two things, u0 and c1, and y is 1, 4, 5. Okay, and we do our normal equation. So you multiply both sides by AT. So AT here, and then you got these two equations with two unknown. So 3, 9, 9, 45 equal to 10, 42. And here we have unique solution because those two columns of A are linearly independent. And you can solve for C0, C1, and that's 4 over 3 and 2 over 3. And yeah, then we find our base least square fit. That's y equal to 4 over 3 plus 2 over 3x. Okay? So, and okay, so now it's a little confusing. And we can also find, we didn't, that's annoying. We can also find bigger things. So this is when we do linear fit, and we can also do quadratic fit. Okay, so if you have okay, so maybe that's right here. So instead of 1, so previously we have y is a linear function of x. So what if we have y equal to quadratic function of x? So y equal to c0 plus c1x plus c2x squared. Then we'll have our matrix that has this 1, 1, 1 for c0, and so x here, and x here as usual, x I, and then we have another vector that's xi squared here. Okay, and yeah, so that's how you do quadratic fit. And so you can solve for c0, c1, c2, and so this is our vector here. So you can see x vector here and the x squared vector here. And yeah, you solve for c0, c1, c2, and once again you have more. You have 4 points, but you only have 3 unknown. And so we do this normal equation, ATX equal to ATB, and now it becomes 3 by 3, and you solve everything, and you find this thing. Okay. And yeah, so this is how you find the base quadratic polynomial, the least square fit of your quadratic polynomial to the data. P of x equal to all these things. And yeah, that's it for 5.3. So basically, you remember your yeah. So I guess the most important thing here is remember the normal equation. So basically, you want to solve for a is equal to b. Oh, sorry. So basically, you want to solve for a is equal to b, but we cannot. So a is not equal to b, so we want to minimize r of x equal to b minus ax, and we have arrow derivation, and the end result is instead of solving a is equal to b, you solve ata x equal to atb. Okay, and yeah, and this will always have solution, and if A has 4 rank, it will have a unique solution. Okay. Yeah, and we see that you can use free curves. Okay, I think that's very nice. We are exactly on schedule. And any question? If not, then yeah, we will have we'll have our class on Wednesday, and we're talking about generalizing all these to abstract space and talk about inner product spaces. Okay, so see you on Wednesday.